Good morning. Welcome to this session on Columnstore indexes. I hope you all had a good time at the party last night. That was a lot of fun. And the Wave is quite an interesting venue. I really enjoyed seeing that too. We're here this morning to talk about Columnstore indexes. So let me start with a little poll to find out who's using Columnstore indexes in production right now. Are you really? Great, and they're working good, right? All right, glad to hear that. Who's testing Columnstore indexes? Anybody? No one's testing yet, okay. Who's been reading about Columnstore indexes? Oh, good, a bunch. All right, that's good to hear. So who's just hearing about Columnstore indexes for the first time today? All right, that's good to know. And now this is a test question. How many of you haven't raised your hands for any of the other questions? A few, okay. And now the real test questions. How many still haven't raised your hands? Yeah. Okay. Okay, so that gives me an idea. There's a fairly wide distribution of what people already know about Columnstore indexes. Let me ask another question. Who's heard of X velocity? All right, that's really good to know. So X velocity is the marketing name that goes with Columnstore indexes. And I was afraid not many people had actually caught on to that, but that's really good to know. But despite the fact that there is this marketing name, X velocity, I'm going to use the term Columnstore indexes in the talk, largely because that's what they're called in the product. You will create a Columnstore index. There's a statement that says create Columnstore index. So we'll use that terminology. Now, I should say that the reason for Columnstore indexes is to speed up applications in the data warehousing context, big queries over large volumes of data. This is not a piece of technology that you'll want to use for OLTP applications. Trust me on that one. But if you're building data warehouses, if you're following a dimensional model like a Kimball design approach, a star schema, you've probably heard that term, or a snowflake schema, then Columnstore indexes can do a lot to speed up your queries. And we're going to talk about why that is in this talk and about how you take advantage of it. So basically, the motivation, which pretty much I just said, is that we want to speed up large queries over large amounts of data. Then after we talk a little bit about motivation, we'll talk about how Columnstore indexes work. We'll look inside a little bit and understand how they speed up the queries. Then we'll talk about how you load Columnstore indexes and some tips for optimizing your schema and index designs in your data warehouses. And finally, we'll talk a little bit about query optimization as well. So on the motivation front, I just have a demo that I want to do to show you why you want to use Columnstore indexes. So I've got this database on my laptop. It's called the Movlia database. Some of you might have seen it in other demos before. It's used a lot in BI demos where they give all fancy graphics and everything. I'm just going to use it because I've got a pile of data there, and I can exercise the engine. So you don't get to see cool graphics this time. But I do have a version of the Movlia database with 100 million rows in it, and I'm running this on this, I think, 4-year-old laptop here. So you might think that query performance isn't going to be super stellar. And in fact, if I'm going to kick off a query, we've got I'll kick the query off and then I'll tell you what it is. So we've got this database. It's got a very large table called the purchase table. That's got 100 million records in it. And then we've also got a table called the media table, which describes the CDs and things that are being sold. I'm sorry, DVDs. These would be movies, right? And I'm doing a join on these two tables, and I'm aggregating by title and seeing how many were purchased. Now, is anybody getting a little bored waiting for this query to run? I know I am. I'm kind of, fidgeting a little bit. If I was a business analyst, I might be thinking it's time for a coffee break, or maybe to go check my Facebook page. This has taken a while, and this is not the experience we want to offer our business users. And yeah, this is only my laptop, but you can imagine with a truly big database on a big production system, queries of this type can still take time. So this took over a minute to run, and I'm not super satisfied with that. Now, what I did in this query was I included at the bottom an option that you'll see there, where it says to ignore the Columnstore index that's on this table. So this is the query response you would get before Columnstore indexes. So now I'm going to run the exact same query, except I'm going to leave off that optimization hint, so to speak. I'm going to let it go ahead and use the Columnstore index that's there on that table. So it's the exact same query. I'm going to execute it. That's a fair point. In fact, the cache effectively was cleared by the first query because it brought so much data into memory that for all practical purposes, it was cleared by the prior query. But it is a fair point. Here, actually, I think. Somewhere up here, I thought. No. I don't remember offhand the statement to clear the cache. But I did that back in the office before I... Sure. Okay, that's fair. Now, it's going to take us a minute, but... So while that's running, maybe we'll can look at something else for a minute. So again, this is without the Columnstore index. We're already at 15 seconds. We got 45 or so to go. While that's running, I'll point out the query or the statement that was run to create the Columnstore index. It will look familiar to anybody who's created indexes before, except we're saying create a Columnstore index. We give the index a name, and we say what table it's on, and then we say what columns we want to include in the index. And that's really it. That's all you have to do to create a Columnstore index. Now, it is a memory-intensive operation. It'll take some time to create a Columnstore index. Okay, so it still took 50 seconds to run that query. And now I'll go back and run it again without the Columnstore index. Even faster. So under a second. Whoops, I guess I didn't turn time on. Okay, we convinced? I hope. Okay, so Columnstore indexes can make a dramatic difference in your query performance. And besides this little demo running on my laptop, there are customers who have been using column stores. Here's a case study that you can find on the FAQ page for column stores. And I'll give a link to this page at the end. The BWin company, which does online entertainment, one example, they had a query that ran 17 minutes to produce a report that when they started using Columnstore indexes, that query ran in 3 seconds. So there are customers, and there's other case studies that you can see online where there's been dramatic performance speed-ups using Columnstore indexes. So that's why we want to use these things. Whoops, wrong button. So let's talk a little bit about how these work. What's going on under the covers when you create a column store index? The nutshell summary is that column store indexes store the data column-wise instead of row-wise. Now, we're used to thinking in the relational world of tables with rows, and that rows are the units of processing. But you've heard in recent years about columnar technology and some very special purpose databases that are built to use columnar technology for data warehousing applications. But SQL Server is the first mainstream database to introduce columnar technology in the core engine. So the idea is that data is stored column-wise. And for reasons that I'll explain a little bit in a minute, that lets us do much, much better compression on the data. So we can fit more data in memory. So we're going to make more use of the memory on the server. But also, very, very importantly, we have less data that we need to read in from disk. And we all know that physical I/O is the stuff that will usually kill database performance. So if we can do less physical I/O and fit more data in memory, then it's going to be a real win in terms of performance. So with that as the overview, let's dive a little bit deeper into what's going on there. This is the basic way to think about the structure of a column store index. First, the table is divided into row groups. We think of that as horizontal partitioning. A row group is about 1 million rows. It's actually 1024 by 1024. Who knows what that number actually is? All right. Okay, some people actually do know that number. These must be real CS people. I didn't know that number, but it is 1024 by 1024, a little over 1 million rows. So that's the size of a row group. And then if you take the data for one column for one row group, that's what we call a segment. So all the data values for one column for about 1 million rows is a segment. Segments can be very highly compressed, and then once that compression is done, that's what will be stored on disk, and that will be the unit of interchange between memory and disk. Now, it should be obvious at this point why we don't use column stores for OLTP applications. If you're trying to update tables, this is going to be a pile of work to uncork these segments and make changes in the data. So you don't want to do this in a transaction context. In fact, you can't do it in a transaction context. But for queries that are reading large amounts of data, your data warehouse queries, this is going to be very, very efficient. So let's walk through an example to kind of illustrate what that looks like in practice. So as I said, the first thing we do is we horizontally partition. So I've taken this data set, and of course this isn't 1 million rows. This is like, 12 rows in a partition. But for illustrative purposes, you can see we first create row groups, horizontal partitioning. Once we've partitioned the data that way, we'll vertically partition, and this creates the segments. And now you can see, as I just said, each segment has just one type of data in it. The first column has only date keys. The second column has only product keys. And you can see how this would be much, much more efficient to compress than just a bunch of random data types. As just one example of the kinds of compression that we'll do, if you look at the product keys, say right here, in this segment, the whole range of product key values is from 102 to 109. So instead of using all the bits to store values up to 109, or even more likely an integer in the traditional way of doing things, for that segment, it can just store the base value, and for each individual record value, it can just store the delta. So it knows that the base value is 102. Then for this record, whoops, where's my pointer? There it is. it's a +0. This is a +4. This is a +7. So it has fewer bits that it has to store for each value. And you can imagine if you apply that kind of thinking and other compression techniques as well across the entire set of data, you'll get phenomenal compression results. And in fact, we do. So once we've vertically and horizontally partitioned the data to create the segments, then each segment is compressed. And they will get different degrees of compression depending on the data types and the data distributions and things like that. But they will all compress. And then the other part of the magic comes in at query time. So the first thing that happens is that because the data is stored in a columnar fashion, we only have to read in the data for the columns that are used in the query. So this query example that's on the screen uses a product key, the sales amount, and the order date key. It doesn't use the other fields. So immediately, half the data doesn't have to be even looked at. We don't have to bring it in from the disk. We don't have to store it in memory. But there's more to it than that, because the query also has a date range associated with it. And so the system can very quickly look at the headers of the segments and realize that nothing in the second row group is going to apply to this query at all. So another half of the data we don't even have to consider. So before anything has ever been read in from disk, 3/4 of the segments have been dismissed. We don't even have to look there. And then for the data that we do bring in from disk, it's this highly compressed data that we talked about before. So it's more efficient for I/O, more efficient in memory. And this is the magic of why, actually this is the first half of the magic of why column store indexes are important. Now, the second thing that I'm going to talk about wasn't even in the title of the talk, but it's got to do with batch mode processing. And this is the biggest advancement in query technology that's happened in quite a while. Basically, data moves through the system as vectors of data in batches. These batches are about 1,000 rows in size, and because the data comes in batches, the overhead per row or per data value is lower. The overhead is amortized over a bigger number of rows. And furthermore, it's highly optimized to take advantage of the cache sizes in the servers. And of course, we get better parallelism when we do this as well. So the basic idea is the groups of about 1,000 rows are being moved. They're optimized to fit in the processor level 1 cache. And then vector operations are performed on the data. Instead of row-by-row operations, it's going to operate on entire vectors. And this will reduce the CPU time typically from 7 to 40 times compared to row-by-row operations. So batch processing is another key advancement that you want to think about. So the number one takeaway from this talk is make sure that most of the work of the query happens in batch mode. Now, here's a question for you. This is a talk about column store indexes. So why is the number one takeaway to make sure that things happen in batch mode? What's the relationship? The parallelism does make it fast, yes. Any other? I'm sorry, could you say it again?
So, because the column store indexes are very logically grouped up records into batches almost in
Bingo. That man deserves an Arc Touch mouse. Come on up and get that. And here, we'll just. Okay, that's exactly right. The column store storage format presents the data in a vector-wise manner already, so that you can process it through in batch mode. And so batch mode is fundamental. It depends on columnar indexing. And I'm going to talk a little bit later and talk about how you make sure your queries are running in batch mode. But that's the number one takeaway. Use these two things together. And if you've got your queries running in batch mode, you're going to see phenomenal query performance. All right. So the next topic is, how do we load column store indexes effectively? I mentioned that data in column stores, obviously you can read it, but you can't update it on the fly. You can, however, do partition switching. Who's familiar with table partitioning in SQL Server? Okay, most of you, good. So partition switching is allowed, and that's probably the most recommended way to load data into columnar tables. But there are three approaches you can use. One is if your table's not too big, you can disable the index, then you can load data into the table, and then you can rebuild the index. You can do partition switching, and if you must be updating data continuously, you can create a delta table and do a union operation. So we'll talk briefly about each of those options. The disable, update, and rebuild is pretty straightforward. I think you probably get that already. You can disable or drop the index. It doesn't really matter. When the index isn't on the table, you're free to update the table. You can do any inserts, updates, deletes that you like, or merges, by the way. And then you just rebuild the index. Now, I say just rebuild the index, but of course, that's going to be an expensive operation. And in general, on really large data warehouses, we'd really rather not be rebuilding the indexes all the time. So the recommended approach is to use partition switching. So you can partition the table. Typically, this will be a fact table in a data warehouse. And let's say that it's partitioned by day. Then each day you can create a new partition, load the new data into a staging table, create the column store index just on the new data, so you're not doing anything redundant, and then do a partition switch to move that staging table into its correct place in the partitioned table. So then it takes its place in the metadata of the system and becomes part of the full table. That method avoids the costly drop and rebuild of the index all the time. But it does happen on, we'll say, a daily basis. Whatever your time interval is, it happens at regular intervals. If you really must load data continuously, then the recommended approach is to have one master table which has the column store index on it, and create a delta table where you can load your updates. So you can do trickle feeds essentially during the course of a day. Then you can, typically you would create a union all over the two tables, and then you've got one view that lets you see your entire set of data. You get column store performance on the big set of data, and you get row by row performance on the daily increments. There is a workaround that you sometimes have to use when doing that, and we'll talk more about that workaround in a few minutes. As I mentioned, building column store indexes is a resource-intensive operation. It'll take CPU time, and it will also take a fair amount of memory when you're creating column store indexes. So typically what happens is that low memory will throttle the performance that you can get in building column stores. It's inherently parallel. If you've got a bunch of segments, it basically kicks off one thread per segment. And if you've got a lot of data, there will be a fair amount of potential parallelism there. But the amount that it can really get is typically limited by the memory that's available. So if you're not building indexes as fast as you'd like, some things that you might consider doing are changing the minimum server memory for your database, changing the size of a memory grant request. I think it's it's by default 25%, and you can maybe bump it up to 50%. Probably an even better idea, if you can do it, is to add memory to the server. You do have the option to omit columns. It uses less memory if you put fewer columns in there. But that's really a false trade-off if you would then be creating other indexes in order to accommodate those columns. And that's a really poor trade-off. But so if you can do it, you want to put all the columns in your column store index. And finally, you can just reduce the amount of parallelism. You can use the max DOP setting if you have to run with less parallelism. A few tips about the design of the database and indexes. So there are a few data types that aren't yet supported by column stores. I won't read them to you, but you can see them on the slide. If you're using those data types, then you've got a few options. You have the option, of course, to omit them from the column store. If you've got, a blob type, you maybe, didn't need it in your column store index anyway, because you're not going to be, querying against the blob itself. For some of the other types, there are some things you might consider. If you can get away with it, maybe you don't need more than 18 digits of precision in your numeric types. If you've got big GUIDs, maybe you can convert those to integers. I won't read everything to you, but there's some things that you can look at as alternatives for situations where your data type isn't supported. Of course, all the most common data types are supported. The things that you would mostly use in data warehouses will be supported. Possibly. Yeah. So now, once you're using column store indexes, then another important consideration is that you don't need a bunch of other indexes sitting around. All the other index types, with the possible exception of a clustered index, are really made redundant by once you've created a column store index on a table. So sometimes having those other indexes there can cause the optimizer to choose a poor plan. So that's one reason to get rid of them. But even if the optimizer isn't making that mistake, you can save a ton of space by getting rid of all those other indexes. And you can save time in your data loading processes by not having to maintain those indexes. So if you're using B trees, it's generally a good idea to dump the other indexes and just use the, I'm not sure I said that right. If you're using column stores, it's a good idea to get rid of the other indexes. Again, with the possible exception of a single clustered index.
But doesn't mean the cluster index is not going to be compressed because it's data?
I'm sorry, I didn't get the question.
When you keep cluster index, does it mean that it won't be compressed when you do column index? Because basically cluster index is data.
So the underlying data is not compressed, but a copy of the data with very high compression is put into the column store index. I think that was what you were asking. Okay. Okay. So there is one case where you very likely do want to create one clustered index in your database. And that's typically on your date column. A lot of queries in data warehouses have a date element to them, or some sort of a time element to them. And if we can put the data into the column store index ordered by date, then that segment elimination is going to be very, very effective. And the column store indexing process will inherit that ordering if it comes from a clustered index. Now, that isn't the only way to do this. You can also partition by date. If I've got, say, daily partitions, then if you think, oh, that's really, really good isolation of values, because all all the data in one segment will be for a particular day if you've already partitioned the data by date. And I will say it doesn't really matter which date you use. If you've got things like load date, ship date, order date. It doesn't really matter. You don't have to stress about which one you use because there's typically a lot of correlation between the dates. And so that natural correlation in the data will give you good segment elimination. Even if the alignment isn't perfect, it will still be very good. Typically, you want to design strings out of column stores. Now, if you're doing a dimensional data warehouse where you've got fact tables and dimension tables, you probably don't have strings in your fact tables anyway. So good data warehouse design practices would have already resulted in a fact table that doesn't have strings in it. But in case you've got one that does have strings, one thing you might consider is creating some sort of a associated table. We typically call that a dimension table. So let's say we've got license numbers in the data, as in this example here. We can create a small table of licenses with a license ID and a license number, and we put the license IDs in the fact table, and we go ahead and create the column store index on that. It'll be much more efficient that way. All right, now the last section that I want to talk about today is optimizing queries. How do we make the queries run as fast as possible? Well, and in particular, how do we detect situations and deal with situations where they're not running as fast as possible? So a couple of best practices, and I'm going to jump into a demo in just a second. Use a star schema. Again, a dimensional design will result in a star schema or a snowflake schema. Put the column store indexes on your largest tables. These will be the fact tables in your data warehouse. And if you can, include every column in the column store index. And finally, make sure you're using integer surrogate keys for the joins between tables. Again, if you're building a data warehouse following the usual best practices, you'll have done that anyway. But for performance reasons, things will be much better if you're using integer surrogate keys. I don't actually know why you would want to do this, other than doing demos like I was doing. But you have the option to provide query hints to force the system to, for example, to not use the column store index. And so those are there on the slide in case you want to know about those. And then here's a few things you should try to avoid using column store indexes. Joining or filtering on string columns will absolutely force it out of row mode and into batch mode. Obviously, joining pairs of very large tables is costly, even if you are using column store indexes. A not in subquery can force it to fall out of row mode, out of batch mode and into row mode. An outer join on the column store and a union all on the column store can sometimes force it out of batch mode. These last three are all things that we're going to talk about workarounds for them in just a moment. But before we do that, let's do a little demo so you understand what to look for in terms of whether the system is using batch mode or row mode. So before we did this query where we grouped by title and looked at the number of purchases of the titles. Whoops. I'm going to do another query. Now, it turns out that there can be more than one media ID for any given title. So for example, a movie may come out on both DVD and Blu-ray, so there'll be multiple media IDs for the same title. So I want to modify that query to include the media ID and the title and the purchase count. I'm going to run the query. Okay, and I'm getting the idea that something's wrong here. This did not run in a second or two. Okay, so here I am thinking about maybe it's time to go check my Facebook page or something. Oh, there we go, 18 seconds. Not the kind of performance we were really hoping for. So let's take a look and see if we can understand what happened. I'm going to look at the execution plan for the query. Oh boy. Okay, so I'm just going to start by looking at the Columnstore index over here. So we see that it did use the Columnstore index. That at least is good. But if I look over here on the right-hand side, you'll see that although we were using the Columnstore index, it was executing in row mode. So something about that query forced the server to execute in row mode instead of in batch mode. And that's not really what we wanted to see. And of course, once it's in row mode, then all the operators along the way are in row mode because the data is being passed into them row by row. However, I know that I can do a grouping on a single column and aggregate the purchase count that way. So what happens if I just, instead of grouping by title, I group by media ID? So it's the same query. In fact, this is the same query as the one I used at the beginning, except it's media ID instead of title. I'll execute that. Okay, I like that. We're under a second executing this query. But let's look again at the execution plan. All right, so it did use a column store. We can see that down here. And if I look over on the right side, it was executing in batch mode. So that did what we wanted it to. Now, if I think about that just a little bit more, wow, this is, okay. So I can still get the query result that I want. If I've got the data grouped by media ID, then I can do another join to reattach the title to it. So it's not quite as simple a query as I might have normally liked to write, but I think I can get the query performance that I want this way. I've made an inner query that runs in batch mode and does most of the work, and I'm going to have an outer query that just reattaches the titles to the media IDs. So let's take a look at that. Oops. Oh, I haven't got the whole thing. Haven't got much room to operate the mouse here. There we go. Okay, that was also very, very fast. So again, it executed in less than a second. If we look at the query plan here, whoops. So it used a Columnstore index. It executed in batch mode. And then if we follow upstream here, I'm going to look for the operators that used most of the resources. Okay, here's a hash match, batch mode. Oh, and another hash match, which executed in batch mode. So this was 40% of the cost of the execution. This was 50, and the Columnstore was 9. So 99% of the cost of the query did execute in batch mode, and that's the sort of thing that we want to see. The query is slightly more complex than I might normally have thought about, but I've gotten it to run entirely in batch, well, almost entirely in batch mode, and we've gotten very, very good performance out of it. So that is kind of the general common theme about optimizing queries to run in batch mode. If you've got something that has fallen out of batch mode into row mode, you see on the bottom, we don't like row mode. What we want to do is find a subset of the query where most of the work can be done in batch mode, and then rewrite the query so that we join to the rest of the data and get the parts that couldn't run in batch mode. And you're going to see in all of the workarounds that I'm about to show you, that's the common theme. Now, before I get into more workarounds, I've got to say one thing. Column store indexes are new in SQL Server 2012. And there are some things that didn't get done that we would have liked to have gotten done. So the workarounds that I'm about to show you, over time, we can expect will not be necessary. The engine's going to be able to do more things inherently in batch mode. So don't think that this is the way we intended it to run now and forever. These are workarounds to some limitations. But most queries run exceedingly well using column store indexes in batch mode. And so I don't want you to think that, well, we'll just wait 2 more releases. The benefits are substantial, and you can get those benefits today. If you just invest, for these few queries that fall out of batch mode, if you invest a little extra time to work around them, there's substantial benefits to be had. So what I'm going to do now is I'm going to walk through the scenarios that we know about where things will fall out of batch mode and run in row mode. To repeat, the number one takeaway from this talk is make sure that most of the work of the query happens in batch mode. The entire query doesn't have to happen in batch mode, but the core parts where the biggest data volumes are, you want those to execute in batch mode. So look for batch mode, and look for it to happen in the places where most of the query time is being spent. Okay, so one thing that we know about, unfortunately right now, outer joins will not execute in batch mode. But outer joins are not that hard to work around, because an inner join runs in batch mode, and then you can do another join to pick up the rest of the data. So I think that you can read the slide and see how the example works. I won't try to go over the whole thing, but the idea is all the rows that had data, all the titles that had data, we're going to pick up using an inner join, and then we're going to do a left join just to pick up the remaining rows where there was no data in the purchase table. So that's reasonably straightforward. And you can see these execution times are for a server that I had in the office. And you can see that, that it really did give good performance once you restructured the query a little bit. In and exists can sometimes prevent a query from running in batch mode. So in this example, maybe I've got a study group. There's a certain set of titles I'm interested in studying. And now I want to do a query where I look by date to see how many sales I had for titles in the media study group. And so I might think about using an in clause to include only those titles. However, as you can see, that will force it out of batch mode. So I'm going to rewrite that query to use a join to pick up just the titles that I want to see. The union all example. This one's a little bit unfortunate because, as you'll recall from earlier on, if you really truly have to do trickle feeds into the database, having some sort of a delta table is the way to do that. And unfortunately, in some cases, a union all joining a table with a column store to one without a column store will force it out of batch mode. So it doesn't always happen. You can see in the first example there, we're grouping by date to see how many sales we had by date. And that ran just fine in batch mode. However, when we added a genre field to the query, for whatever reason, that forced the engine out of batch mode, and it ran considerably slower. So for a union all, the workaround, it's more wordy, I'll admit. There's a lot of text on this workaround, but it's not really that hard to understand. We're going to do a query on the main table and get the subset of the data that comes from the main table. We're going to do another subquery on the delta table, get the chunk of data that comes from there. Then we're going to do the union all inside the query. And because we're doing grouping, then we'll regroup again in the combined query. So yeah, it's a fair amount of text, I agree. But conceptually, it's not that hard to understand what's going on. And as you can see, once we've gotten it back into batch mode, it ran very fast.
So why don't we just
Watch for the next release. Like I say, we just didn't get everything that we wanted to. Scalar aggregates. This one's kind of bizarre, but for some reason, an aggregate without a group by doesn't get batch processing today. This one truly escapes me, why that would be. But it is the case. So the workaround is to add a group by, and then just sum again. I know it sounds kind of funny to say that, but it works. And by the way, what I'm doing here is I'm trying to be very honest. These are the things that we know about. There are some things that aren't as we wished them, and I'm telling you about all of them. So it's...
you can't use the range.
Pardon?
With the sum, you can't use the range. You need the range, don't you? How can you count by D would be the range to the rest of the blocks?
Yes.
Can't use the range.
What? Can't use a range.
We can't use the range because the sum is only count stuff. What range is it going to use? Can't say, oh, this block has got this set of dates, this block has got this set of dates, this block has got this set of dates.
Because it's a Columnstore, you do usually have to use a count. You do give it S6 for stars, for example.
I'm sorry, but at the moment I'm not quite following the question. So okay, let's come back to this afterwards. It worked. I really ran this query. Okay, let's come back to that. I'll be happy to talk to you about it afterwards. Okay, I hope this is the last one. Multiple distinct counts. Multiple distinct counts are a problem anyway, right? Regardless of whether or not you're using column store indexes. Because the server has to take the data, run through it and generate a spool, a temporary table, and run through the data twice. And then, unfortunately, spooling becomes a single-threaded operation. And so multiple distinct counts in SQL Server in general are a kind of a pain. Now, the good news is that SQL Server does just fine with one distinct count and any other number of non-distinct aggregations. So it's only when there's multiple distinct counts in the query that SQL Server gets into trouble. But again, following the same logic that we've been talking about, it's not all that hard to work around it. You do two subqueries, one to create each of the distinct counts, and then you join those together. And if you think about it, that actually means that we're going to scan the column store twice, once for each of the subqueries. But column stores are so much faster that it's absolutely worth it to run through the column store twice to create the two distinct counts. So that's the last one, right? Yes, good. Okay, so those are the cases that we know about. You can see there are a fair number of them, but they're corner cases. And we've tried to illustrate how you work around those when you do run into them. And so we're hopeful that will help you manage the cases where you do run into those things as you start to work with column store indexes. So to summarize, column store indexes plus batch mode processing can give you amazing performance. This would be unlike anything you've seen before with SQL Server or really any other relational database. Column and segment elimination go a long ways to reducing the demand for data that has to be brought into the system. And then you combine that with the fact that the data you are bringing in is compressed, and the performance can be just absolutely outstanding. There are 3 methods for dealing with the read-only property of column stores. You can drop, update, and drop the index, update the data, and rebuild the index. You can use partition switching if you've got a partitioned table, and that, again, that's the most recommended solution if you can use it. And then you've got the union all method with the main table and a delta table. And then we talked about some workarounds for some special cases that today force the query engine out of batch mode. We recognize those are a pain. They're unfortunate, and the team is already working on fixing those things in the next release. But like I said, don't wait for the next release to start using column stores, because the performance gains are so outstanding, you really want to take advantage of that. So there's a couple things I want to point you to for more information. Eric Hansen, a program manager on the engine team, has written a column store tuning guide that covers most of the same points that were in this presentation, but in a nice document that you can refer to. And there's also an FAQ on column stores, which includes links to customer case studies. So you can see that there are real customers who are using and benefiting from column stores today.
Sorry, can everybody hear me? Can I please add we do have in New Zealand our own case study, means that runs in production, column store index in production at the moment. If you're interested what we've done and how we implemented it, please go to Microsoft Release Studies website and search for BNZ and currently Bank of New Zealand.
All right, thank you. All right, and then the last thing is, please do fill out an evaluation. It helps me to know what I'm doing well or not doing well, and hopefully we'll see you next year and give an even better talk. So thanks very much for your time, and I will try to answer a few questions. I see we've got a couple of minutes left in the hour, so.